Swayam Prabha. Digital India. Educated India.
I welcome you once again to this lecture on flow through porous media. What we were discussing was the Ergun equation as an alternative to Darcy's law, particularly when you have full information of the particles that are constituting the bed, the porous bed. So now we said in the lecture that I am going to in this next round of video lecture, what I am going to discuss is a special case where a porous media may not behave exactly the way we thought it would. So what is that? What kind of exception we can have? So let us talk about it in this lecture. So what we have here is a process which is known as fluidization. A process which is known as fluidization. What is exactly fluidization? Let us say I have a packed bed, and here we have these. So I have these particles, and these are constituting. So these are all filled with particles. And we are having a flow, let us say we have a flow rate of Q over the overall cross sectional area is, let us say, A. So superficial velocity is Q divided by A, that is the superficial velocity. So that there is a flow from the bottom, and the flow is taking place and flow is going out. And then if you have this as length L, and if you see there is a pressure drop delta P across this bed, so one can find out, one can apply Darcy's law, or one can apply Ergun equation to find out what would be the how pressure drop is related to the flow rate. So now suppose we continue to increase this velocity or increase this flow rate. So if we increase this flow rate, and if we do not have a restriction that this porous medium is to be held as it is, in that case what we expect is what is shown here in this plot. So here you can see in the x axis it is the superficial velocity, and the y axis for this particular line we are talking about pressure drop. So let us say we are plotting pressure drop versus superficial velocity. We have already seen, we have walked with Darcy's law, where we said that we talk about pressure drop versus flow rate, and we will get lines, and we pass a line, regress the line through the center, and to find out this the slope, and from that we find out what is the permeability of the bed. So in this case also we can expect, when we are plotting pressure, so pressure will increase with superficial velocity, it will increase. But how long? Generally we are operating here, so we can see that it is linear. We are happy with it, with that, and we find out what is the slope and what is the permeability accordingly. But if you go beyond some threshold value of this superficial velocity, one will find that the pressure drop will not change any further. And if simultaneously, if somebody plots bed height, this is bed height. So if y axis is the bed height as a function of superficial velocity, one finds that the bed height was all along constant. We always said it is L, and L is constant. I mean, when we define Darcy's law. So this was L, and L was constant all along. But beyond this threshold value, I mean, these here there are some innuendos. It will not be a very smooth transition. There would be some curves, some humps, etc. I do not want to get into that, but overall trend is that the bed height that we talk about here, this bed height was constant all along, but beyond this point one sees that the bed height starts increasing with superficial velocity. What does that mean? Now the bed height is changing, but pressure drop is not changing, pressure drop remains constant. So what that means is this bed is expanding, this bed is expanding. So this bed, once it was some length, now it is at a higher length. If you do not have any constraint on the top, the bed will simply start expanding. In fact, this is one way these filters are cleaned. I mean, if one runs, say for example, somebody is working on a gravity filter. For example, if you have a sand bed and continuously pouring water, and water contains a lot of suspended solids, you want to get rid of those, so muds, all mud and all those. So you expect those muds to be those suspended solids to accumulate at the nook and cranny of these pathways here, and what we get is filtered water. So that time the flow is from top to bottom. Why top to bottom? Because one uses the gravity. So by gravity the flow, so you don't need any external pump or anything, simply pour water. I mean, that is how filters work a lot of times. You simply pour water, and because of gravity water simply drains, and whatever suspended solid is there, that is held up in this bed. After some time this bed would be this all those pores, most of them pathways would be all restricted. Okay. So at that time one needs some cleaning. So at that time a practice is that there would be a blow from the bottom. So once they blow from the bottom, then you can expect this bed to expand. This bed to expand, that means all the mud or all the suspended solids that has accumulated in between. So those suspended solids now during this reverse flow, you expect that since the bed has expanded, so earlier one particle, another particle was sitting here, another particle was sitting here. Now in the expanded form, this is here, this is here, this is here. So naturally whatever was accumulated there, now if you give a high reverse flow, these accumulations, they will be carried to the top and will be separated. So now once again the bed would be cleaned. Okay, so this is something which can be done. This is called back flushing. So now this creates a very important situation here. This process of the bed getting suspended. So that means flow. So we are coming back to fluidization. So when we have this fluidization, that means we have put this flow and then it has crossed this threshold value. So at that time these particles in the bed, they get suspended. Okay. So this condition, this is known as incipient fluidization. That means the fluidization has set in. So if you continue to increase the flow rate, you will see this bed would be expanding and there would be movement of these solid particles, and then what is the end of it? I mean, if you continue to increase the flow rate further, then these particles will be simply carried downstream. These particles will go out of the system, and in fact this is one situation, this is one technique which is used in a process which is known as pneumatic conveying. Grains, instead of putting them in the sack and carrying separately, the grains can be stacked in a chamber, and there could be a high flow of air, and this would be carried, then this entire bed will be then fluidized, and then these grains will be carried downstream to wherever you want to take it, just in this by establishing a airflow. So this process is known as pneumatic conveying. So that is the end of it. So if you continue this process, so at the end you will find these would be simply conveyed through the pipe. These particles will be conveyed through the pipe, and it would be just a two-phase flow in that case. Solid, grains and air, they are flowing together through a pipe to a destination where you want to take it. That is known as pneumatic conveying. So now this fluidized bed, they have certain advantage. The advantage is something like this, that a lot of times these packed beds, they are used used to conduct catalyzed reactions. So, suppose A and B, they are fed, so they are put in a packed bed, and this packed bed, these are basically in that case catalyst pellets. Catalyst pellets means these are, you can think of tablets. Inside that catalyst material is loaded, and the fluid that is flowing through these packed bed, they will come in contact with that catalyst, and they will be this A plus B forming C plus D, and this reaction is catalyzed. So, this kind of packed bed packed bed of catalyst is very common. Now, one found that instead of working on a packed bed where the catalyst pellets will be all together, so there would be some places you may not have access fully or have full control over the flow. Instead of that, if one works on a fluidized bed setup, that means where the catalyst pellets are suspended, then one can access these catalyst pellets even better. So, that is how there is this famous FCC unit, which is fluidized catalytic cracking unit, which is used in many petrochemical complexes. You must have heard FCC unit. So, there instead of having catalyst as packed bed, one prefers to work with fluidized bed concept. So, where the particles are suspended, but they are not leaving the chamber, they are simply suspended. So, how would you theorize this type of a process? Earlier we said it was a packed bed, and we had Darcy's law, we had Ergun equation and all this. So, now when you have this fluidized bed, what are the conditions? How would you explain it? So, what they have done here is, first of all, they said that the pressure, so the point incipient fluidization, where this is the minimum fluidization velocity, this is where fluidization starts, and fluidization continues for some time until this entire bed is simply carried downstream, that is pneumatic conveying. So, that is down the line somewhere, pneumatic conveying will happen. So, in between this entire superficial velocity here is basically, here it is, the bed is in fluidized state, but the fluidization process started here. So, this is referred as VOM bar. So, this is the superficial velocity at which the fluidization has started. So, this is called minimum fluidization velocity, or this is same as, this is the concept is same as incipient fluidization velocity. So, that is the point where fluidization started, and if somebody wants to look at or find out what is that velocity, one must make note of the fact that on one hand you have, so this point belongs to this line, right. So, on one hand this point has to satisfy Ergun equation. So, that is what we have tried to, we have written here. So, on the right hand side I can see the Ergun equation for delta P by L. So, if you leave out this part, on one hand we are equating delta P by L with this quantity, which is the Ergun equation. On the other hand, now we have a new definition of delta P by L, that is what here given here, pressure drop across the bed has to be weight of the bed per unit cross sectional area, allowing for the buoyant force. That means, at the time of when this is fluidized, think of a particle. If this is the particle, this particle has a weight. This is this particle that is constituting the porous media, one of these particles, it has the weight. It is already suspended in a fluid medium, because flow is taking place from the bottom to top. So, there is already a buoyancy acting on this. Okay. So, weight of the bed per unit cross sectional area, allowing for the buoyant force. So, there would be a buoyancy which is acting upward, weight acting downward. So, what would be the corresponding force? And that force per unit area, that would give the pressure drop. So, from there if you can come up with a delta P by L. So, one has to make sure that the delta P by L that you are putting here by you are obtaining by Ergun equation, when that delta P by L becomes equal to, that pressure gradient becomes equal to the pressure gradient that could suspend a particle. That means, this pressure gradient is sufficient for this particle to support, basically weight minus buoyancy, whatever force is acting downward, the delta P by L because of the flow should cancel it, then only this particle will get suspended. So, the pressure drop across the bed from that concept would be weight of the bed per unit cross sectional area allowing for the buoyant force. The volume of the solid is AL into 1 minus EPSA. Volume, total volume is AL, out of that solid fraction is 1 minus EPSA. So, AL into 1 minus EPSA, where EPSA is the porosity of the bed. So, delta P would be in that case AL 1 minus EPSA, that is the volume of the solid, multiplied by rho P, which is the particle density, that means solid density. So, multiplied by rho P into G, that is weight downward, minus there would be a buoyancy acting upward, and buoyancy is the weight of the fluid of same volume as that of the particle. So, that means minus AL 1 minus EPSA, that is the volume of the particle, into rho this time, not rho P, that is the rho is the density of the fluid, into G. So, this is after accounting buoyancy, this becomes the total force acting on the particle. Okay, weight downward, buoyancy upward. So, that divided by area A, area is the cross sectional area A. So, that gives you, so this is not just for one particle, this is for sum of all particles. So, this is the volume of all the particles and multiplied by their buoyancy corrected weight and divided by this. So, this is the buoyancy corrected weight of all particles divided by this cross sectional area. So, this gives you the delta P. So, once this delta P is supported by the delta P that you get by Ergun equation, then at that point one can say that this incipient fluidization will start. So, then this delta P by L is, one can cancel out this A with A, this L will be here at the denominator. So, delta P by L would be simply G into 1 minus EPSA into, so this is arising from here, G into 1 minus EPSA into rho P minus rho. So, that is exactly what is this delta P by L. So, therefore, at incipient fluidization, on one hand this delta P by L has to be this much, that means the pressure drop that the system has, that pressure drop should be sufficient to suspend the particles, that pressure drop should be sufficient to overcome the gravity with the buoyancy correction. So, that is on one hand, that is to be true, and on the second, this pressure drop is where this pressure drop is arising from. This pressure drop is arising from Ergun equation, and these two are to be equated. If one has to find out what is this VO bar. So, if we equate these two, the VO bar that we solve, one has to solve for VO bar, and if VO bar is solved, then the VO bar that one finds out, that VO bar would be equal to this VOM bar, which is the superficial velocity for incipient fluidization. Let us now look at, so what they have done here is, for very small particles they have broken it down. Okay, we had this Ergun equation, it has on the right hand side two terms, right, because they did not want to work with VO bar square and VO bar and all those. So, instead of that, so only in one case they have only worked with 150 divided by RE porous media, that term. So, only the laminar flow term in Ergun equation was used. So, when this was used in equating this two term that we mentioned just now, so one found out that this should be the VOM bar, 150 I can see is appearing. Whereas, if you do not work with this laminar part, if you want to work with the second term, which is 1.75, friction factor is 1.75, I can see 1.75 is appearing here. So, one finds out that this is the term. So, you have this is the superficial velocity at incipient fluidization if is working with very small particles. So, there would be this because after all REP has this dP term. So, dP is if the diameter of the particle is very small, whereas if the limit of very large sizes, when the diameter of particle would be much larger. So, this is contributing, very small particle is taking you to the Reynolds number of porous media small, and in this case Reynolds number of porous media large. So, these are the two cases, and for that you have the corresponding incipient fluidization values. So, by looking at these parameters, one can very well say that, well, if you want to expect this bed to be fluidized, at least you have to take the superficial velocity to this level, that is given by this expression. See, on the right hand side what you have, basically particle density, fluid density, and particle diameter, and then sphericity factor if any, and of course, the porosity of the bed. So, that is something which is now porosity of the bed will remain same all along until the incipient fluidization. So, this is the initial porosity of the bed epsilon. So, at that incipient fluidization, these would be the superficial velocity. So, until you cross this superficial velocity, there is no scope for fluidization, that is for certain. Now, in this context, one important matter is that we said that this pressure drop would be going like this, and then then the fluidization starts, and then at one point there would be pneumatic conveying. So, if one's interest is to run a fluidized bed, then one needs to know what is this window, right? Because if incipient fluidization starts and immediately it starts becoming the pneumatic conveying comes in. So, then or immediately at this point pneumatic conveying develops. So, then one gets a very small window. So, what that means is, if there is a slightest fluctuation in superficial velocity, and that can happen due to many reasons. So, if there is a slightest fluctuation in superficial velocity, the entire bed will be simply running out, moving away from the system. So, that is not wanted. One wants a good window over which this window for this fluidization velocity. So, even if there is some perturbations to this fluidization velocity, still the fluidized condition will remain, it will not go to pneumatic conveying condition. So, to ensure that, one must look at what is the settling velocity of a particle. So, a particle, if you leave it as it is, if you leave it in air, this particle will have a settling velocity. That means, first of all, this particle will be accelerated because of gravity, particle will be coming downward. So, and on the other hand, when the particle is coming downward, there would be buoyancy, of course, it is acting upward, plus since the particle is moving downward, there would be this drag force acting upward. So, once particle, if you leave it from the rest, it will accelerate, and beyond some point you will find that these three forces that we are talking about, one was gravity, one is buoyancy, and the other is drag. So, these three forces, gravity is downward, buoyancy upward, and drag is upward. These three forces, they will balance each other. How they will balance each other? Because as the velocity increases, drag force increases. So, as the drag force increases, this will counter the gravity. So, at one point velocity continuously increases, drag force also increases, at one point they balance each other. So, at that point the forces are all balanced. So, that means the net force acting on this particle is 0. So, in that case the particle will not change, it will not accelerate anymore. That is called terminal velocity of the particle. So, particle will continue to move downward at the terminal velocity. So, if one needs to work here and one needs to work with a good window, so one must compare what is the terminal velocity of these particles as against what is the superficial velocity that you are imposing, and how the superficial, where the superficial velocity stands with respect to the terminal velocity. If superficial velocity and terminal velocity, they are very close, one can think of I mean that possibility that particles may get carried away and will not remain fluidized. So, one has to ensure that there is a good gap between the terminal velocity and the superficial velocity, so that the fluidized condition can be retained. So, here we have done the same thing here, settling velocity of particles. This is given by, see, first of all, mass into acceleration for any particle with mass m and u is the velocity. So, du dt is the acceleration. So, mass into acceleration, that gives me the force on the particle, that is essentially mg, which is the gravity force acting downward, minus m rho by rho p into g. This is m by rho p is the volume of the particle, rho p is the particle density, m is the mass of the particle. So, m by rho p is the volume of the particle multiplied by rho, which is the density of the fluid. So, this is volume of the particle multiplied by density of the fluid multiplied by g. So, this is essentially buoyancy. So, this is buoyancy. So, weight of the particle minus buoyancy minus drag force. So, drag force is given by, there is something called drag coefficient. There is something called drag coefficient, which is known as CD. So, drag coefficient into so drag coefficient, I mean it is covered in fluid mechanics. This is something like this, that this drag coefficient is a very similar term as friction factor. Generally, the drag force is drag force divided by the projected area. Projected area means for a sphere the projected area is a circle. For a rectangle, for a cube, this projected area is a square, something like this. So, if there is a fluid flowing, and if you have a particle here, so the drag force would be the projected area would be the area that the fluid sees. Okay. So, this is for a sphere, it would be a circle. So, force divided by projected area, this projected area is defined as AP in this expression, this AP, force divided by projected area. So, this is equal to drag force, the drag coefficient CD into u square by 2, the velocity kinetic head basically, and into rho. So, it is basically, you can think of this CD, which is called drag coefficient. This is very similar to friction factor. So, this also can be plotted exactly in the same way as a function of Reynolds number of the particle, this time not a porous media, Reynolds number of a particle, and particle Reynolds number is given by particle diameter, particle velocity, rho of fluid, viscosity of the fluid. So, that is how the particle Reynolds number is, and typically this also is inversely proportional to particle Reynolds number. This is 24 by Re particle Reynolds number. So, this is called drag coefficient. So, just like we had that time, delta P is equal to delta P by rho in case of pressure drop through a fluid. Delta P by rho was F L by D V square by 2. So, here also we have this projected area. So, this gives me the delta P. So, delta P, here also we have this delta P, where delta P by rho would be equal to C D into u square by 2. So, this is it is a very similar expression. So, this is what is utilized here. So, this is essentially the drag force. So, now if we equate this, and if we set this term to be equal to 0, that means when these it has reached the terminal velocity. So, then ut at du dt equal to 0, this can be simplified as this expression 2 into g into rho p minus rho into m divided by this quantity AP, rho p, CD and rho. So, now this ut divided by VOM bar, that I have been saying here, that we need a window, this ut should be much higher compared to VOM, so that we get a longer window. So, ut by VOM bar, this should be as large as possible and preferably greater than 100. So, that if there is any fluctuation in the superficial velocity at the time of when it is in fluidized state, it should not reach the terminal velocity that it leaves the system. So that small particles do not get carried over. So, on slightest change in velocity above VOM bar, this will happen if this ratio is not high enough, and high means at least to the tune of 100. Now, here if you can see these UT, what is this terminal? So, if VOM bar, we have already found out what is VOM bar. We have already gotten this expression of VOM bar here. We have another expression depending on the size of the particle. So, we have already gotten this expression for VOM bar. How to get this UT? We have already arrived at an expression for UT, but this expression requires information of M, information of AP, and information of CD. The other terms are known, rho p, rho, etc. Rho p is the particle density, that means the solid density. The porous medium is consisting of solid particles. So, that solid density is rho p, rho is the density of the fluid, g is the acceleration due to gravity. So, these are all known to us. M here is the mass of the particle. Mass of the particle is volume of the particle multiplied by the density of the particle. Volume of the particle is 4/3 pi r cube or pi by 6 dp cube. So, if you write it in terms of diameter instead of radius, so pi into dp cube by 6 multiplied by the particle density. So, this is the M, and AP is the projected area. Projected area in this case for a sphere, it would be pi r square, and pi r square is given as pi dp square by 4, where dp is the particle diameter, right. So, projected area means this, as I said, when there is a fluid flow, the sphere, the fluid will see a circle. So, that is the projected area. So, MP is known, AP is known. So, now CD. Now, CD has, on one hand we said that if you are in laminar region, it comes to 24 by RE. So, CD can take this value, or CD can take 0.44, which is the, it is that constant value that in case of porous medium we have 1.75, right, F versus REPM. There we have this 1.75 term. So, here it is 0.44. So, it depends on whether you work with this regime or this regime, the corresponding terminal velocity will take this equation, g dp square rho p minus rho divided by 18 mu, or terminal velocity will take this if it is in the if it is in this region of particle Reynolds number. So, it either of these will happen. So, it depends on which region of particle Reynolds number one is in. So, these are the two expressions for UT that are available. So, the job here would be first calculate this VOM bar. If somebody wants to design a fluidized bed system, first calculate VOM bar, find out the VOM bar, and then simultaneously one needs to look at what is the terminal velocity, what is the size of the window over which this fluidization will occur. So, this is extremely important, and so you have to parallelly find out what is the terminal velocity and take this ratio and see whether this ratio is sufficient, at least to the order of 100 or not. So, this I think this gives you an give you this entire exercise, this gives you and feel how this fluidization will occur, where the fluidization will take place, at under what conditions, and how you can predict where the fluidization is going to take place and where the fluidization would be stable enough, so that it will not get carried downstream. So, this is all I had here as far as this particular lecture module is concerned. So, we had talked about packed bed, we have talked about Darcy's law, and then we said that if we have good information, the particle size, etc., the Ergun equation, its subcomponents and everything. And then we said that the one offshoot of this is this fluidized bed instead of a packed bed. And then if one needs to find out at what superficial velocity this fluidization sets in and how, under what condition this fluidization would be stable. So, we have some handle over it. I mean, how to predict these cases, these situations. We have talked about that in this lecture. So, here I am closing this lecture on flow equations, and I will start a new concept altogether from the next lecture. Thank you very much.